So one of the ramifications of the photoelectric effect work was that it showed that light could behave like particles. And in fact, it could behave like things that had mass. They could influence an electron. You could think of the photoelectric effect as having uh, uh, photons come in and actually collide with the electrons in the metal and knock them out. Made this is actually the way Einstein thought about it, and it has the same physics as an inelastic collision that causes momentum to be transferred. And so all of this basically says that electrons are massive particles that can be influenced by light, and so it made light seem like light was made up of particles. And this led to Einstein coining the term photon for each of Planck's quanta of light. So a photon was the small indivisible particle of light that was proportional to the frequency that Planck had put in his theory. So E equals h c over lambda. So each of these would be now a photon in the Planck theory. Of course, Einstein was also at that same time working on the theory of relativity. And so the notion that light could carry momentum was interesting because, of course, in relativity, the famous equation is that E equals mc squared. And so now if we look at what happens when we set these two equations equal to each other, okay, so you can set them equal to each other and you can write hc over lambda equals mc squared. And if you rearrange this and cancel everything that cancels out, you end up with a different equation, which is that lambda equals h, Planck's constant, over mc. Okay, and this may not mean a lot to you if you haven't taken physics, but mass times speed, right? This is now the nominal mass. We learned that light doesn't have mass, but m times c, the speed, so the mass times the speed, this quantity in physics is called the momentum. So this now rationalizes the momentum of light. And we can see that if light can influence a massive particle and cause it to be like an electron, even though it has a very small mass, it's still massive. And so if light can cause those electrons to be ejected from inside of a metal, then the light must be transferring momentum to them. And sure enough, here's a way to actually quantify that. And there was another set of experiments called Compton scattering, where basically if you take X-rays and you shine X-rays at a beam of electrons, they actually scatter the electrons. They act like the X-rays impart momentum and change the trajectories of an electron beam. So there was a much more clear example of momentum transfer between light and mass and massive particles, in this case the electrons. And that goes even further in that the electrons can in turn scatter the X-rays. So it was sort of a mutual interaction. And that got a very brilliant young man named Louis de Broglie to thinking, well, wait a minute. What stops us from writing the following? If we're saying now that light can carry momentum and behave like a massive particle, why can't we flip that on its head? And why can't we say that a massive particle like an electron has a wavelength? And we would just write the same thing, except of course an electron doesn't travel at the speed of light. It travels at some velocity, which we're going to call here v. I started to write nu. All right, so mv. So, and so this was his proposal. He actually put this in his PhD thesis and said, I think this is true, and I think that it explains what's going on in Compton scattering, and I think it also explains why the Bohr model behaves like it does, because if the electrons have wavelengths, then the way that they travel in orbits is restricted. And we talked a little bit about that in class. And so de Broglie had some really brilliant ideas around this, and they turned out to be right. And so now we call this wavelength here the de Broglie wavelength. And if we study this equation carefully, we can see that it is only in very special circumstances where the wavelength of a massive particle becomes big enough for us to notice, right? Normally these wavelengths are very, very tiny, and we'll actually do a calculation to illustrate that. But when we're talking about very, very light masses, okay, so since h is a really tiny number, remember that's h is 6.626 times 10 to the minus 34 joules times seconds, which is an almost unimaginably small amount of energy times seconds here. On a macroscopic scale, if we wanted to think about, the energy associated with a baseball or any other massive object that we would encounter in everyday life, that would be, joules or tens of joules or maybe millijoules. But 10 to the minus 34 joules is almost unimaginably small compared to that. So the only time we are going to be able to get that into the realm of observable wavelengths that are appreciably different from zero, is either when the mass is very, very small, so we need to have a tiny mass, and the velocity can't be too high, right? We want this to be very, very small as well. Right? So as soon as the denominator starts to get big, then essentially the wavelength is going to disappear. It's going to become so small as to disappear. But when we're talking about very tiny masses, like with electrons, and when we're talking about very, very low velocities, okay, so a slow electron is likely to have a more appreciable wavelength than an electron that's traveling very quickly. Okay, and so this all works because it explains why, when we go down to something like the electronic scale, we see clear evidence of the wave nature of electrons. But when we're dealing in our everyday world with things like pencils and baseballs and marbles and peas and whatever, we never see those things have funny wave-like behavior. They just act like they're particles all the time. We can't see their wave-like nature because the wavelength, according to de Broglie, is so tiny. And so it's helpful to do a calculation to illustrate that, and that's how I'm going to finish this video. So let's start off by using this equation to calculate the wavelength of a tennis ball. 60 grams, and it's traveling at 150 kilometers per hour. Okay, and so that's about the fastest that you can hit a serve. No, 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 no. Bad, bad, bad. Stop, stop. So let's use the de Broglie equation to calculate a couple of representative examples. The first thing we're going to do is we're going to calculate the de Broglie wavelength for a macroscopic object, a tennis ball. So if you serve a tennis ball at 150 miles an hour, what is the de Broglie wavelength going to be? And so what we can do is we can convert 150 miles an hour into metric, and that becomes a velocity of 68 meters per second. And we're going to use for the mass of the tennis ball 60 grams, which is 6.0 times 10 to the minus 2 kilograms. Okay, and so now when we plug all this into the de Broglie equation, what we're going to get is that lambda equals 6.626 times 10 to the minus 34, and I'm going to write joules, but I'm going to expand it out. Remember, joules are composite units that are kilogram meters squared per second squared, and then that's going to be times seconds. And we're going to put down here our mass, which is 6.0 times 10 to the minus 2 kilograms, and our velocity, which is 68 meters per second. Okay, so now we can do our dimensional analysis and make sure everything cancels. This kilograms on the top cancels down here. The seconds in here is going to cancel out one of the seconds in here, and then the other one's going to go away because of the seconds down here, right? So this is in the denominator up here, this is in the denominator down here, so those both cancel, and then this meters is going to cancel one of those meters, and lo and behold, we're left with the right units, meters, but not a lot of them. It's going to come out to about 1.6 times 10 to the minus 34 meters. So that's the wavelength, the quantum wavelength of a macroscopic object like a tennis ball when it's served at a speed of 150 miles an hour. And it's tiny. And that's good, right? We know that tennis balls never behave like waves. They behave like solid particulate objects. We never see any wave-like character for them. And that's because they have it, but it's just so small that it could never even be measured. This number here is not significantly different from 0. And that's why nobody ever noticed that objects moving around in the world that we observe with our eyes have wave-like character, because all these wavelengths are far too small to affect the way that they move when we're watching them. It was only that when we got the ability to make measurements on really tiny objects with very small masses like electrons that this wave-like nature became evident, became measurable, and started to affect our observations. So let's see how that actually plays out if we switch now to an electron. And so the mass of an electron is mass of an electron is 9.11 times 10 to the minus 31 kilograms. So before we had 6 times 10 to the minus 2, now we have 9 times 10 to the minus 31. So it's about 29 orders of magnitude smaller. Okay? And we're going to say it's traveling at the same velocity. So now when we plug this in to our de Broglie equation, and I'm not going to do all that stuff with the units again. You've seen it once. That's enough. Okay? When I plug this into the de Broglie equation, we're going to expect the corresponding wavelength to be about 29 orders of magnitude larger. And so now we're talking about something we can actually see. Okay? And so when we work out all this math, what we find out is this now becomes 1.1 times 10 to the minus 5 meters. All right? So that's big, right? That's 1/100th of a millimeter. Okay, that's something you can actually see with your eyes. The smallest dust grains that you can see are on the order of a few tenths of a micron. Okay, which is exactly what a few tens of microns, which is what we're talking about here. And you can certainly see things that are tens of a micron in size. Remember, a micron is 10 to the minus 6 meter in a microscope. So now, if we were going to be making observations of electrons that have a wavelength that's on the order of microns, we would expect that to very clearly manifest itself in measurements if they were sensitive enough. So again, this is supposed to just be an illustration of why the quantum mechanics could be this beautifully correct theory that nobody ever noticed until we started to really look into the substructure of atoms, the subatomic particles, electrons. Once we started making measurements on things that had such small masses, we couldn't help but notice this quantum strangeness of their behavior, and the theory then, because the measurements were made carefully, the theory kind of developed around all of this new data from this new size regime that we could finally explore.